Hello, and welcome to the third lecture of this year's Qiskit Global Summer School. My name is Ibrahim Shehzad, and I am part of the quantum algorithm engineering team here at IBM Quantum. In this lecture, we'll build off what you learned in Lecture 2 and understand in more depth what it means to program a quantum computer. So let's dive right in. So the outline for this lecture is as follows. We'll start by discussing the Bloch sphere. I'll define what that is. It's a handy representation of an arbitrary quantum state. From this, we'll branch off into discussing arbitrary quantum operations and the digital gate set that suffices to implement them. We'll then touch on the notion of depth of quantum circuits, which is something that largely determines which quantum circuits are capable of delivering useful results on existing hardware. Finally, we'll move on to some hands-on programming where we'll put all of these concepts to use. So recall that a qubit, as you've heard in previous lectures, is a two-state system. And a two-state system with complex coefficients has 4 degrees of freedom. Quantum states, however, are constrained by the fact that they must be normalized, that is, their norm or their magnitude should be 1, and that global phases do not matter. These two constraints bring us down from 4 to 2 degrees of freedom, which then implies that an arbitrary quantum state can be represented by a vector that lives on a two-sphere. This sphere is exactly what is called a Bloch sphere, and this then implies that an arbitrary quantum operation on a qubit can be represented as a rotation parameterized by two angles that are labeled here, theta and phi on a two-sphere. So here I've given an expression for ket psi, an arbitrary quantum state, and as you can see, it's entirely determined by two parameters, theta and phi, which are angles on the sphere. Now, rotations about the three axes given here, x, y, and z, are generated by the Pauli x, y, and z matrices. And this is why these Pauli matrices come about so often in quantum computing when you're programming quantum computers. And you'll see them over and over again over the course of this course as well. So the Pauli gates that I just referred to, x, y, and z, are a subset of single qubit gates that we use to implement single qubit operations. Along with the identity gate, they form a basis for single qubit operations, as is clear from the Bloch sphere rotations that we discussed on the previous slide. There are other interesting gates as well, actually. So for example, we have the Hadamard gate, which we use to generate superpositions of quantum states, as well as S and T gates. Here you can see on the left how each of these gates is represented in Qiskit. Now, since a quantum state can be represented as a vector with two entries, you can also think of these operations or gates as matrices that act on these vectors. Here on the right, you can see them represented as matrices. But you cannot do arbitrary quantum computations that involve multiple qubits with just single qubit gates. You can, however, do them if you add in 2-qubit gates. And so an interesting 2-qubit gate that you encounter a lot, for example, when you're entangling qubits, is called the C0 gate. The C0 gate generalizes the notion of a classical bit flip to the quantum realm. Here on the right is how you represent it as a matrix. Now note that since this is a 2-qubit gate, its matrix form has to be able to act on a 4-vector rather than a 2-vector. And so this is why it's a 4x4 matrix, as you can see on the right. Another useful 2-qubit gate is called the controlled Z, or the controlled phase flip gate, which is actually the 2-qubit gate that is implemented natively on IBM's latest Heron processors. And what this effectively means is that if you run a quantum circuit on an IBM Heron device, the 2-qubit gates in your circuit will always be converted into a combination that involves controlled Z or CZ gates. Let's now synthesize what we've learned so far about single and 2-qubit gates into a series of statements that'll be useful for us to remember as we delve deeper into quantum computing. So firstly, an arbitrary quantum gate, and this can be a 3-qubit gate, a 4-qubit gate, or even higher, can be formed using only single and 2-qubit gates, which vastly simplifies the number of gates you'd need to deal with on a daily basis if you program a quantum computer. Then, an arbitrary 2-qubit gate can be decomposed using C0s and rotation gates on Bloch sphere. This gives rise to the notion of a universal gate set. So effectively what that means is a minimal set using which you can represent any quantum gate, literally any quantum gate. Now there are several equivalent bases for a universal gate set, but a particularly useful one is formed by the C0 gate, the Hadamard gate, and the T gate. There is an important subgroup of the group of universal quantum gates. It's called the Clifford group, and a basis for this is given by Hadamard gate, C0, and the S gate. And a really important theorem in quantum computation that deals with these gates is called the Gottesman-Nil theorem, which says, and I'll gloss over some of the technical caveats here, but effectively that any circuit involving only Clifford gates can be efficiently simulated on a classical computer. So for these circuits, for Clifford circuits, you would not necessarily need to even use a quantum computer. What this means then is to actually see the value of quantum circuits executed on quantum hardware, we must focus on circuits involving gates that sit outside of the Clifford group. And so, for example, circuits involving arbitrary rotations fall into that category. Having learned about single and 2-qubit gates and universal quantum gate sets, which are the building blocks of quantum circuits, let's now briefly discuss what kinds of circuits are best suited to the current hardware. Now, as is well known, quantum gates implemented on actual hardware have certain error rates. To demonstrate this, I've pulled actual data from the IBM Quebec quantum processor. Here you can see this in the top left corner of your screen. And as you can see here, the median 2-qubit gate error for the hardware native CZ gates is actually an order of magnitude higher than the median 1-qubit SX gate error. As you can also see on this diagram, the 2-qubit gates take longer to implement. What this means is that the overall error profile of your quantum circuit is largely determined by its 2-qubit gate structure. So in particular, if you have too many 2-qubit gates on the current hardware, the error rates will add up fast. Also, since these gates take longer to implement, the time taken for the 2-qubit gates to finish implementing can start to compete with the coherence time of your qubits. Now let's distill all of this. What this effectively means is that on current devices, while we can certainly run circuits involving hundreds of qubits, in terms of depth, it is the shallow circuits that yield the best results. And what this translates into concretely is order 100 layers of 2-qubit gates and around 10,000 2-qubit gates that can be effectively implemented on the current hardware on most of the IBM QPUs. Actually, on all of them, I would say. With techniques like post-selection, configuration recovery, and error mitigation, actually, this number can be increased even further. And I'd invite you to look at this document that I've linked at the bottom of this slide for more details on some of these error mitigation and error suppression techniques. Now, this feeds into our narrative behind what we consider useful quantum computing. So to be able to move past what classical computers are capable of doing and to achieve scientific breakthroughs, we have to scale to larger circuits. In particular, it is circuits that sit in the high qubit medium depth regime that are capable of delivering the best results. So the high qubit count typically takes you beyond what classical computers can easily handle, at least with exact or brute force methods, and the medium depth requirement keeps you within the boundaries of what a quantum computer in this day and age can handle well. And how do we scale up in practice? We do this by following this trajectory here. Effectively, we try and go to a high qubit count while keeping the depth contained in the early stages of our exploration. This is the regime where existing quantum computers work the best and where classical computers will generally struggle. And then as we develop the hardware more alongside, error mitigation techniques, we can push this frontier further towards quantum advantage. What we want to avoid doing when we program quantum computers is getting stuck in the low qubit regime down and at the bottom left, because that regime is typically where classical computers will suffice, and you would not even need to use a quantum computer. So having discussed this theory, let's now move on to some hands-on coding with Qiskit, so you can develop more of a feel for what it means to actually program a quantum computer. So I'm going to start off by building some basic circuits And let me do that as follows. I'm going to import some libraries to begin with. Let's get here. Import, save. The reason for these imports will become clear in just a second. So let's call this circuit QC1. It's going to be a very simple circuit involving just 2 qubits, and this is how I build that circuit. So I've imported this quantum circuit object from Qiskit. I've specified the number 2, and this is going to build a 2-qubit circuit for me. Now let me start adding gates, because at this point this is just a skeleton for a circuit. It's entirely empty. There are no gates in it. But the way I do that is as follows. So I'm just going to choose to add an X gate on the first qubit. Here, first represents the 0th qubit. We start counting from 0. I'm going to then add 3 C0 gates as follows. So I'm going to add a C0 between the 0th and the first qubit, then a C0 between the same qubits, but now I'm going to flip it. So the control bit will now be the one, will now be the first one. And then another qubit, another CX gate between the same 2 qubits. Let's do the following, and I'll clarify why I need to do this. But let's do save underscore state vector. And let's run this as follows. Let's actually see what the circuit looks like. And so what you can see is it's a simple 2-qubit circuit. I have some initial states, and the qubits Q0, Q1. Q0 gets acted on with an X gate, and then I insert these 3 C0s. Now, the point of this exercise is actually to show you that there are a few different ways in which you can implement the same gate. So let me now do the following exercise, and you'll see why I made this claim. Let me set up another circuit on exactly 2 qubits again. And this time what I'm going to do is I'll put an X gate on the 0th qubit, and then I'm going to put a swap gate between the 0th and the first qubit. So a swap gate does exactly what it sounds like. It swaps the 2 qubits effectively. Now, why did I do this? I'm going to claim that actually this circuit is logically the same as the circuit above. So QC2 with these operations is logically the same as QC1. And how do I justify that claim? I'm going to do, actually I made a typo here, so let's do the following. This has to be QC2. Let me also add this instruction. Basically, it'll record the state vector state of the circuit. Okay, I made a typo here. Let's save underscore state vector. Let's plot it out, because it's good to always visualize these things. This is what the circuit looks like. So this is a swap gate, as you can see. All right, so now to my claim that these 2 circuits are logically the same. Let me import an air simulator, which is what I do to simulate my circuit. I'm going to define this object as follows, so that it does a state vector simulation. Okay, so having instantiated the simulator object, let me now do simulator.run. Actually, I can read my mind, Copilot. Let me actually call this result underscore 2. I'm going to turn this off so that, I can write my own code. Simulator.run QC2 result. So this will effectively pull the results of a state vector simulation, or just a simulation for now, let's say, done on these 2 circuits, calculating these objects. I'm going to then do result underscore 1 dot get underscore state vector and compare it with result underscore 2 get underscore state vector. So you can see that the state vectors that I got at the end of simulating these 2 circuits are the same. That's basically consistent with the fact that these 2 circuits are logically equivalent. And the point of doing this exercise was basically to show you that there's many, many different sets of gates, and some of them are effectively logically equivalent. And what this exercise is showing you is that a swap gate here is logically equivalent to inserting 3 C0 gates here. This is actually something that's an important fact to remember. Basically, because when you run quantum operations on hardware that has limited connectivity, when you want to implement a 2-qubit gate operation, you often have to insert swaps to move qubits adjacent to each other so that the 2-qubit operation can be implemented. However, effectively, what that translates into, as you can see here, is that you get 3 2-qubit gates each time you have a swap. In this case, it's exactly 3 CNOT gates. And so each swap sort of adds to the cost of your circuit. And that's what this exercise was supposed to demonstrate. All right, let's now move on to another quick exercise, and we'll call this, let's name this something like creating entanglement belt states. Okay. And how do I do that? I'm going to basically, again, set up a quantum circuit, but before that, I'm going to import a visualization library. That'll be handy. Let's plot histogram. Okay. And let's call this QC_ent because it's going to demonstrate entanglement. It's quantum circuit. It'll just be another simple object on 2 qubits that's represented here. Let me add now a Hadamard to the 0th qubit, and let me add QC_ent. Add a C NOT gate between the 0th and the 1st qubit. So this is, let's just run this and see what we get. This is what this circuit actually looks like. As you can see, this is what I intended for it to be. Now let me actually go back because I do want to measure this circuit. So I'm going to add some measurements to the circuit. We can plot it again. And now you can see that there's these two measurements that have been added. Okay, why am I doing this? And you'll see in just a second. So let me do, again, a simulation of this circuit. I'm going to say simulator.run. Simulator was something I instantiated above with the air simulator. I'm going to simulate QC_ent, and I'm going to set the number of shots to be, let's just say, what number do I want? Let's say 10,000. Okay, so this is setting up the job. If I want the result, let's call it result_ent. It'll be something like this. And then once I've pulled the results, I can plot the counts that I got from sampling from the state. So this is effectively going to set up my circuit, which sets up a quantum state, and then I'm taking measurements 10,000 times on that state. So to get the counts, which tell me which bit string I measure how many times, let's do the following. So result_ent dot get_counts. And then I can go ahead and plot these counts with this plot histogram object that I retrieved earlier. All right. So this is what I get. As you can see, the state that I set up, I've sampled, the 00 bit string and the 11 bit string roughly the same number of times. There is some, shot noise here, which accounts for the disparity. I've taken a finite number of shots here. But this is consistent with the fact that this is a belt state. There's, of course, other tests you can do to ascertain that, but this is one quick check of it. And the other thing to note here is my quantum circuit was actually on 2 qubits, which means that the possible bit strings I can measure are 00, 01, 10, and 11. So those are the bit strings that exist in my solution space. However, I'm only sampling 00 and 11, which is consistent with the fact that my state was just a superposition of 00 and 11, which is the belt state. All right, so let's now move on to another exercise where we discussed the notion of a Bloch sphere in the theory part of this lecture, I guess. Let's actually try and play around with it and actually build a Bloch sphere. So I'm going to import some libraries again, and the reason for this will become clear in just another second. Let's snooze this. And I do from Qiskit.visualization import plot_Bloch multivector. I'm going to do an import from matplotlib .pyplot import figure, and what else do I want to do here? Let's do matplotlib inline. Okay, now let's just see. Okay, I may actually not need this figure import, but we'll come back to it. I'm going to set up a reference quantum circuit, again, on just 1 qubit this time. Let me add some operations to it. And so I've built a 1 qubit circuit, added a Hadamard operation on it. I'm then going to do a Y rotation by an angle of pi divided by 2 on the 0th qubit. Then to be able to do the simulation and retrieve the state vector, I'm going to add this line here. And finally is simulator.run qc_ref result dot get underscore state vector. Actually, yes, qc_ref qc_ref. All right. So this is one thing I wanted to do. I am going to set up another circuit in parallel just to be able to show you what's going on. And let's see, qc_ref. Let's add a Hadamard again to the 0th qubit. Dot save underscore state vector. And finally, I'm ready to run this as well. So this is a separate state that I'm going to run a simulation on. Simulator.run qc_ref2 dot result get underscore state vector. All right, now let's actually plot this out. So I'm going to say figure 1 is Bloch multivector, and I'm going to do state 1 dot show, and then at the same time I'm going to do the same thing for qc_ref2. What I'm calling it after the simulation is state 2, so fig2 dot show. All right, so there's a lot that's going on here, so let's unpack this. It turns out that I actually did not need this import, so let me get rid of it just for clarity. I set up 2 quantum circuits. My first quantum circuit is on 1 qubit. I acted with the Hadamard, and then I did a rotation around the y-axis. On the second circuit, I just put a Hadamard and did nothing else, and then I simulated these circuits and obtained the state vectors that I get at the end. That's what this line and this line does, and then I just plot them on a Bloch sphere. All right, so as you can see, effectively what's happened is the second circuit with just the Hadamard acting on it, put my state here on the Bloch sphere, okay? And this was my state. Now, if I went ahead and in addition to the Hadamard acted with an RY rotation by pi by 2, as is done in this circuit, you can actually see that my Bloch vector has rotated around the y-axis, right? So it's gone from here to the south pole. And this is just meant to show you how you would actually visualize a state on a Bloch sphere in practice. And you can also visualize how this rotation has actually happened. So you can visualize what this additional RY operation did for you in this case. Okay. All right. So let's now move on to one more example. We can give this a handy name as well, so that we remember visualizing rotations on the Bloch sphere. Okay. All right. So one other exercise that I did want to do today is basically, given a circuit, I want to be able to decompose it into, it's into a certain basis gate set, and then look at the number of 2-qubit gates that I get in the final circuit. And you'll see why that's useful in a second. This will tie back into our discussion on depths and number of 2-qubit gates. So let's do the following. I'm going to do from Qiskit transpiler. I want to program myself from Qiskit.transpiler import generate preset pass manager. I'm going to retrieve a backend. I instantiated service already, so I'm just going to use IBM Quebec. And then what I want to do is define an object called generate preset pass manager against this backend. And optimization level is 3. So basically, this object here is something that I will use to convert my logical circuit into the native gate set of the IBM Quebec backend. And you'll see how that's done in a second. This optimization level 3 is basically saying that I want my circuit to be as optimal as possible. I want the best decompositions. Let's actually build a circuit. We can be ambitious this time. So let's go up to something that has 20 qubits, because why not? And we do the following. So I'm going to put a Hadamard on all of my qubits as follows. And then I will put C-naughts between a few sort of nearest neighbors. For I in range 10, let's do QC.CX, I plus 1, and QC.CP, so controlled phase gate, 0, and actually the phase that I want to insert is, let's just pick this to be 0.1. All right, is there anything else I want to do? Yes, this is wrong syntax, need indentation. Okay. Let's see what the circuit actually looks like. I have not transpiled it yet, but this is what my circuit actually looks like. So I just, kind of just put Hadamards on all of them and then C-naughts and controlled phase gates on some of them. I can actually do a little bit more. Let me put controlled X and controlled phase gates on all of my qubits, or between all of my qubits. Now we need to fold this a little bit so you can see the whole thing. But now you can see that there's now sort of this ladder of C-naught and controlled phase gates going all around. So this is my logical circuit. This is my starting point. Now to convert this circuit into a device native gate set, what I will do is I'll call this XP_QC. XP is a term we can use for, let's say, transpiled, and then pass manager.run on QC, and this will basically transpile my circuit. Let's do a few quick checks with this. So let's say that my initial circuit, let's count how many non-local gates it had. It had 38 2-qubit gates. We can count this here. What does my final circuit after transpilation have? Let's say that we have local gates. So 19. So some of the optimization has actually condensed the size of my circuit. Let's actually see what the circuit looks like. So xp_qc.draw PL fold -1, and then I'm going to set idle wires to false so that, effectively this is now a circuit that's mapped onto the entire device. So it'll be on 156 qubits in this case, but only 20 of them are active in this case. I'm just going to set idle wires to false so that I don't visualize any of the empty ones. And this is what my circuit now looks like. So as you can see, some of these gates have been, actually, let me do the following. Maybe this is easier. As you can see, some of these gates have now been decomposed, right? So I had Hadamards, but now those Hadamards have been converted into these gates. These are now the device native gates. All the 2-qubit gates have been changed into entirely CZ gates. So again, this is a representation of my circuit entirely in terms of the basis gate set of the device. Another thing you can see here is when I transpiled my circuit to IBM Quebec, in this case, when I put it on the device, my qubit 19 from my logical circuit mapped onto qubit 0 of the QPU of IBM Quebec, qubit 18 mapped onto 1, and so on and so forth. So let's go back here. Now, a few we check the number of 2-qubit gates. Let's also do the following. This is a handy number to always check for any of your circuits. So now draw, I want to calculate its depth, and I'm interested in the 2-qubit gate depth of the circuit, so effectively the number of 2-qubit layers. And it's basically telling me that XP underscore QC has 19 layers of 2-qubit gates. Okay. So effectively, this is the circuit I started off with. I transpiled. This was my logical circuit. I transpiled it. This is what I end up with. And the point of this is just to demonstrate to you a quantity that you should always check whenever you put your circuit onto a device, because as we discussed in the theory part, the depth is generally something you want to keep contained. And you can use, optimization techniques to help you do that. All right. So let's see. I think that is basically all I wanted to cover in this hands-on exercise. And let's just give this another name, because just to say, consistent with everything else, let's say we call this counting 2-qubit gate depths. Okay, so this basically is everything I wanted to do in this hands-on exercise. One thing we can actually do here is actually go back and simplify the circuit. So I'm going to remove all my controlled phase gates and just put, C naughts. So this is the circuit I have, the logical circuit. I can go ahead and transpile it, and then I can go ahead and visualize it. This is what it looks like. The depth stays the same in this case. Now, the point of doing the second exercise was to give you a bit of a hint to what comes next, and this is something I'll leave for you as an exercise. So if I go back up here, as you remember, we set up a belt state on 2 qubits. And what I'd invite you to do as an exercise for yourself is, if I wanted to set up a state that is a uniform superposition over 4 qubits, how would I create that state? So let's call this challenge extension. I want this to be a markdown cell. Gives a challenge. Can you build a circuit that produces a uniform superposition over 4 qubits? Okay, and everything we've discussed in this tutorial should actually already give you the tools to do that. So I'd invite you to try out this exercise. So this marks the end of the hands-on part and effectively the end of our lecture. Before we conclude, I'd like to point you to the IBM Quantum platform, where you can find a plethora of interesting courses to take you further on your journey as a quantum computing practitioner. There's also an interesting tutorial that I'll point here in the second line, second blob, that goes more into the depth of some of the other single qubit gates that you can implement in Qiskit. And then finally, looking ahead, in the next lecture of the summer school, you'll build on what you've learned in this lecture and supplement that with concepts like entanglement and an important theorem that underlies quantum information theory and quantum error correction called the no-cloning theorem. So with that, thank you for your time, and I hope you enjoy the rest of the summer school.